Okay, I've told you in the past that metals plastically deform through the sliding of close-packed planes like this. And I also hesitated, though, because I said there's actually one additional level of complication to it, or not complication, but there's a different mechanism. This is not exactly how metals plastically deform. So let's take a look at that now. And, and what I want to do is I want to consider a single crystal of a material. So I've drawn a little rectangular solid there. And what we're going to try to do is we're going to try to cleave this thing in half. And so let me illustrate what I mean by that. We're going to apply a force. Okay, we're going to apply a force to this here and here. And then what we want to do when we apply the force is observe it starting to deform like this. Okay, and so if we did that, you can imagine that we would we could calculate the theoretical requirement for that force if we knew the area and we knew as well what was going on at the interface here. So what I want to do is do one of these little call-outs here and say, let's consider that interface, all right? And I told you it's a single crystal. So a single crystal is going to have, some highly organized lattice of atoms. Don't get too hung up on exactly how they're organized here at this point. This is the type of thing I'm talking about. I don't need to draw them all in necessarily, but there's some kind of a lattice of atoms. To help make that a little bit more clear, I will draw in sort of the nearest neighbor, or the bonds between atoms, if you will, and we'll explore this in more detail later. But what's important is what I'm just drawing in there. There's some bonds that span across that that area, that cross section. So if we knew the area and we knew the bond density, that is how many atoms, per unit area, and you could work that out from some knowledge of crystal structure, and the bond strength, you could calculate the theoretical value for the strength required to deform the crystal, right? It sounds pretty good. If this was our model, we could do that. And decades ago, that was actually performed. And the problem is that the theoretical strength that was calculated, theoretical, okay, technically this is a shear strength, but anyway, it's the theoretical strength was way over. It's about, it's about 5 times what the actual strength was. 5 times more than experimental. Okay, so you can do an experiment, perform this test and validate your model, because this is a model. Is this how metals plastically deform? And it's off by 5 times. So clearly there's something wrong with this understanding here, this model of deformation. So this is actually inaccurate. There's something else. There's a different mechanism going on, and that's what I'd like to show you now. So what I sketched over here with this crystal structure is not entirely the whole story. So what we actually often we observe a huge quantity of in crystals is this. So I'm sketching this out so you can sort of follow along, but right now you don't necessarily see exactly what I'm trying to illustrate. So if I sketch in the nearest neighbor atoms here, that is the direction that the atoms are bonded to one another, you'll start to see where this imperfection is. Okay, so it's a certain type of imperfection, but it's a crystalline imperfection. And I like to use the word imperfection rather than defect, although you will hear defect used as well, because defect sometimes has a negative connotation to it, and these imperfections, there's many of them that we'll explore, are often used to achieve the properties that we want. They're hugely important in every application of engineering. So these imperfections always exist, but now here's the beauty of it. Watch this. So this is our crystalline imperfection, and what we're trying to it's a certain type. We'll explain what type later. It's called a dislocation, but we'll explore that later. What we're doing is we're applying a force now, like I said, and what these imperfections allow us to do is this. If you watch the, see, I just break that one bond right there, okay, and then that bond reforms. Well, now where's the imperfection? You know, which one of these things is not like the other, right? There's which one? Well, this one seems to be missing a rule of atoms, whereas a moment ago it was this one. Okay, so I break one bond, and well, in fact, this is coming out of the page and into the page, so it's really a row of bonds. And I could break another one through the application of this force, and then it reforms. And now where is this imperfection? It's moved over again, right? It's moved over step by step. So the end result is actually still the same, that this plane of atoms has moved to the right, this one has moved to the left, as we illustrated up here. That is to say, this start and end position is correct, but they don't all move together like this. There's actually these imperfections that allow just one row of bonds to break at a time and reform. Again, if I can kind of animate this a little bit in a very basic way by just undoing here and going back and forth. So there's what we started with. A bond breaks, another bond breaks and reforms. And it's that step-by-step movement of bonds that is the mechanism for plastic deformation. So it's a step-by-step breaking and reforming of bonds. And reforming of bonds. That is the correct mechanism for plastic deformation in a metal. And now now that we understand that, right, that the beauty of this, right, it's only good if you can apply it. But now that we understand this, well, there's so many things we could do. What if I went and I put a carbon atom into the lattice like that, and it's going to interact with that movement? Is it going to make it harder? It's going to make it easier. Well, sometimes it's going to make it harder. It could make it stronger. That's the mechanism for alloying. And so what we'll do in the next few videos is explore different types of imperfections, and a lot of times we're going to tie it back to how it interacts with this crystalline imperfection that is the basis for plastic deformation. Because I think plastic deformation right now is an easier property to wrap our heads around. We'll get into some electrical properties later on, but mechanical is a good one to wrap our heads around to introduce these imperfections. Okay, thanks a lot.